Non-Turing-complete ledgers, like the XRPL ledger, are highly optimized for secure, low-latency value transfer, but that architectural simplicity intentionally excludes the complex logic required for decentralized finance, isolating billions of dollars from the programmable EVM ecosystem. Bridging that gap manually introduces severe user friction. First, users are forced to manage separate cryptographic seed phrases for entirely distinct network architectures. Second, generating and storing new EVM private keys expands the attack surface, requiring users to secure new vulnerabilities they may not fully understand. Finally, execution on an EVM chain requires the user to acquire and bridge native gas tokens simply to process operations. Flare smart accounts address these structural limitations through a specialized implementation of account abstraction. The protocol deterministically maps an external XRPL address to a unique smart contract wallet on the Flare chain. By removing the requirement for direct EVM key management and gas token acquisition, dormant, non-programmable capital can securely interact with high-yield DeFi environments. That mapped contract is the personal account. It acts as the execution nexus for the user on the Flare network. Control over this personal account is permanently anchored to the user's originating XRPL signature. The EVM contract will only accept instructions mathematically proven to originate from that specific XRPL wallet. Because the XRPL cannot directly push data to an EVM state machine, the architecture requires an off-chain relay actor. This actor is known as the orchestrator. This maps the Flare architecture empowering the orchestrator. The layered hierarchy moves from the Flare time series oracle up through the data connector, assets, and smart accounts. The orchestrator relies specifically on the Flare data connector to verify external chain events. We are going to deconstruct the off-chain orchestrator paradigm and examine the precise VMA and TypeScript optimization stack that makes trustless cross-chain execution possible. This architecture shifts the computational and financial burden of EVM execution completely away from the end user, placing it onto a specialized, trustless relay network. The orchestrator operates as a relayer, a transaction builder, and a proof delivery mechanism. It monitors the origin chain and executes the user's intent on the destination chain. The system processes these requests through two primary architectures. The first is the proof-based flow. The process initializes when a user sends a payment transaction on the XRPL to a designated gateway address monitored by the orchestrator. That transaction incorporates a 32-byte payment reference. The first byte acts as the instruction opcode, identifying the specific type of cross-chain action. The second byte designates a wallet identifier for partner platforms routing the transaction. The remaining 30 bytes are packed with the specific action parameters required by the smart contract. Once the transaction is confirmed, the orchestrator detects the payment and submits a request for a payment attestation proof to the Flare data connector. Following verification, the orchestrator delivers this FDC proof to the master account controller contract on Flare, which validates the data and dispatches the execution logic to the user's mapped personal account. Because the master account controller requires an enshrined cryptographic proof from the FDC, malicious actors cannot spoof execution intents. The on-chain state will only update if the external transaction actually occurred. The second architecture is the direct minting flow, which optimizes specifically for bringing non-smart contract assets onto the EVM. This schematic details the F-Assets protocol. Here, the XRPL payment is routed directly to the F-Assets core vault instead of a secondary gateway address. An off-chain executor observes this payment and triggers the execute direct minting function on the F-Assets Asset Manager contract. Upon successful minting, the asset manager initiates a callback to the master account controller, depositing the newly minted wrapped assets into the user's EVM vault. During this callback, the system automatically deducts the necessary gas and execution fees directly from the minted F-Assets. By utilizing the direct minting callback and automating the fee extraction, this architecture dramatically reduces the off-chain coordination overhead for high-volume gateways. Executing these flows at scale requires specific developer tooling. The ecosystem has largely migrated away from heavy, stateful legacy libraries like ethers.js. The current standard for Flare smart accounts is the Flare VM Starter codebase, which relies entirely on TypeScript and VM. VM separates network communication into specialized clients. The public client handles horizontal scaling for read-only state lookups and event pulling. The The wallet client manages transaction signing and broadcasting, allowing the orchestrator to execute on-chain state changes using pre-funded hot wallets. This code displays the concept of state diagnostics. An orchestrator must inspect the on-chain state and predict transaction success before spending gas. The diagnostic sequence programmatically verifies if the XRPL mapping exists, queries yield vault balances to ensure sufficient collateral, and checks the protocol's health for active pauses or rate limits. By relying on VM's reactive event filters and log parsing utilities, the orchestrator processes finalization events in real time, eliminating the need for complex indexing databases. For systems submitting high volumes of cross-chain transactions, strict static typing and parallel read operations are strict requirements for maintaining gateway resilience. Requiring a user to input a precise 32-byte binary memo for every transaction introduces significant execution risk and user friction. The protocol solves this via the minting tag manager and dynamic tag manager. A user reserves a sequential destination tag, represented on-chain as an ERC-721 NFT. The user then binds that tag directly to their personal account. The owner of this tag can invoke the setAllowedExecutor function, which establishes a strict 10-minute execution cooldown window. This execution lock guarantees that only a designated private orchestrator can process transactions arriving with that destination tag, protecting the user from public mempool front-running. Beyond standard minting, Flare Smart Accounts support advanced programmability using custom EIP 4337 packed user operation structures. These custom operations are delivered through two mechanisms: opcode 0xFE, an off-chain hash commit that minimizes source chain fees, or opcode 0xFF, where the full execution payload is stored directly in the XRPL memo. The synthesis of dynamic tagging and EIP 4337 operations allows an external ledger to orchestrate arbitrary DeFi composability from a standard mobile wallet interface. Operating an orchestrator requires capital. Node operators must continuously pre-fund hot wallets on the Flare network to submit execution proofs. To prevent this from becoming a capital drain, Flare Smart Accounts feature a built-in gas and fee monetization architecture. The first compensation path relies on dynamic flat executor fees. The orchestrator queries these parameters via Veeam batch requests, matching their gas settings to real-time protocol costs. This flowchart breaks down the second path. In proof-based workflows, after the system base fee is covered, any remaining collateral reservation fee is routed directly back to the executor's hot wallet. The integrity of the orchestrator is enforced by Zelic-audited on-chain validations. These physical safeguards ensure the executor cannot submit malformed proofs or alter the execution path of the user's instructions. By combining automated cost recovery with strict liability isolation, the system ensures the orchestrator model remains economically sustainable for independent node operators. This operational security scales directly to institutional custody providers. They utilize this architecture to maintain assets in XRPL cold storage, while simultaneously accessing Flare's decentralized finance liquidity. For advanced financial applications like decentralized dark pools, Flare Smart Accounts are combined with trusted execution environments. The hardware enclave manages private trading states, while the orchestrator syncs the cryptographic proofs to the public ledger. This map illustrates the network synergy. The orchestrator relays transaction data, relying entirely on enshrined verification oracles like the Flare data connector to validate reality. Through this entire complex execution chain, the user retains absolute self-custody of their assets. By abstracting the friction of multi-chain execution into a verified programmatic layer, the orchestrator paradigm establishes the foundational infrastructure required for a truly autonomous, trustless machine economy.